from yes. I'm sorry, what doesn't?
Yesterday you said that principle of superposition doesn't apply for
Right,
large deformation problems.
right.
Is that applicable even if the structure is elastic, large deformation elastic problem?
Yes. I think his question, I will repeat the question. Yesterday I said that the principle of superposition does not apply for large deformation problems. It does not matter whether the structure is elastic, viscoelastic, plastic, makes no difference. Okay, to show you that, so I will answer your question in equation form. That way you will be better convinced why it's like that. So if so we start from the reference configuration, and this is a point P which occupied place X in the reference configuration. Now if you say first twist it, torque, then this point will go to say P prime. Now you stretch it, or you apply pressure, or you some other kind of loading, and it moves to this final position, say P double prime. So what is the, and this is the displacement u2. So u, total u equals u1 plus u2, right? It's a vector addition. And if I am writing in component form, so I will say u a or ul equals u1 plus u2 of a. And our expression was E L M equals, or I can just put 2 here instead of dividing by 2. So I have delta u a over delta x, sorry. So it's delta u l over delta x m plus delta u m over delta x l. So that is the small deformation part, plus delta u say n over x m delta u n over delta x l, and that's the contribution coming from the nonlinear term. Now if you substitute u equal to u1 plus u2, we will get so that's the term from u1. And then we will get a similar term, so it's plus similar term from u2. So these two terms we can copy again, except replace u1 by u2. Is it okay? Now will we get another term or not? See, here is the problem. So you will substitute u equal to u1 plus u2. So there will be 2 terms here and 2 terms here, and if you multiply 2 terms by 2 terms, you get 4 terms. 2 we have included here, and the ones that we have not included will be un1 over x differentiated with respect to x l, u n 2 differentiated with respect to x m plus u n 1 2 with respect to x l, u n 1 with respect to x m. So, this part is, you can say, ELM 1 from displacement 1. This part is from displacement 2, and these two terms will not will not appear, right. So, the principle of superposition does not apply. We did not say the material is elastic or plastic. We have not said a single word about the material of the body. So, whatever we are doing or whatever we did yesterday, including this expression, is applicable for elastic, viscoelastic, plastic, any thermal problem, you can say thermally induced strains, any problem you like. We have not talked about the material property yet. So, same thing will be true for most of what I will say today. We have not talked about material yet, because we did not even say what is the material of that body, whether it is copper, steel, aluminum, rubber. I mean, it could be water, but in fluids we do not talk about strains, we talk about strain rates. So, that is why I am hesitating to use the word fluid. In a fluid, it is very difficult to find the reference configuration. I say it is difficult, but it is not impossible, because we do molecular dynamics for fluids problems also. So, it is possible. Is it okay? So, what about now if I were to work in terms of deformation gradient? I think that was one of the questions you asked me. Well, that was the question you asked me. I think life is a little simpler than trying to remember that it's E1 plus E2 plus these terms. So, if I were to work in terms of the deformation gradient, I will say F total, which is my F, say that will be FIL equals delta U I over delta XL plus delta IL, which is really equal to delta XI final, which is 2 over delta XL. The deformation gradient is you differentiate the final position with respect to the initial position, and if you wish to work in terms of displacement gradients, then this is Kronecker delta plus the displacement gradient. So, let's just keep this one then. So, that is the total deformation gradient, right. Differentiate the final coordinates with respect to the initial coordinates, and most of us or all of us know chain rule of calculus. So, this is xi2, you differentiate with respect to, you differentiate this with respect to this, and then this one with respect to that. So, the chain rule says the chain rule of calculus says that you differentiate this one with respect to x1 and then x1 with respect to xl. These little x's like x1, x2, x3, they are functions of big x1, x2, x3. These are functions of these. So, I can differentiate these with respect to those and then this with respect to that. Chain rule, I mean, it's not a, there is nothing new in it. So, what happens then, what can I call this quantity? So, this is Fij and this is 2 and this one is Fjl. So, this is 1. So, it is easier to say then F equals F2 F1 in matrix notation. So, it is the first deformation gradient pre-multiplied by second deformation gradient. You apply this first, that is what we did here. In going from here to here, we applied the deformation gradient F1. In going from here to, sorry, in going from this place to that one, we applied deformation gradient 2. And then you applied F1 first, and then you applied F2. You cannot switch the order, that is the problem. You cannot say I will say it is F1 F2 because matrix multiplication does not commute. So, that thing we have to remember, that it is F1 F2 here, otherwise you will get totally wrong answers. So, this is easier to conceptualize than remembering. I mean, I am using the word remembering, but you do not have to remember anything except the definition of F. So, from this F you can find C, and from C you can find E. Okay. And again, as far as the principal strains are concerned, find eigenvalues and eigenvectors of C. So, eigenvectors will give you directions along which principal strains, along which stretches are maximum or minimum, and then this stretch itself, eigenvalues of this are squares of stretches, not stretch, and stretch is final length over initial length. So, that I think that is what we covered yesterday. Besides this, we covered rho, sorry, not we did not talk about balance of mass. So, we also talked about that volume little dV over big dV is J, which is the determinant of F. And we said determinant of F we assume is positive, because volume cannot become negative. I mean, and so the ratio of two volumes cannot become negative. So, if we make this assumption determinant of F actually, before I even talk next, any other question you wish to ask? Any other question you want to ask from the material we went over yesterday? Okay. So, incidentally, so if you want to talk about strains, you can use either F, C or E, and you will see there are other possibilities also. So, there are many strain tensors, and Professor Seth, he used to teach here long time ago, before probably I was born, so certainly before you were born, and he introduced many definitions of strains also. So, they are called Seth tensors. Not many books mention that. Trussell's books, that is where I learned from. Trussell books talks about Seth tensors, but if you see many other books, actually, as far as I know, I have not seen that result mentioned in any other book on continuum mechanics except Trussell's book. And I done. I'm sorry.
It's also there on Wikipedia.
Oh, well, Wikipedia somebody might have put it, yes. Yeah. But Wikipedia, I don't know whether I can call it a book or not, yes. And please don't trust everything on Wikipedia. even though I use it myself. But Wikipedia is written by people like you and I. There is no sense, nobody reviews it, right? So there, and they do mention at the bottom that it has not been reviewed by anybody. Okay, so there will be some more coming, more strain tensors coming. Okay, what?
Seth was in the maths department, right?
I'm sorry.
Was in the mathematics department.
He could have been in the mathematics department. Yes, actually, yes, you are right. He was in the mathematics department. But you know, mathematicians do mechanics too, right? I mean, you can say this is mechanical engineering or civil engineering or aerospace engineering, geological engineering, ocean engineering. I mean, ocean people, if you are using a vessel that you are designing a ship or a submarine, they do in ocean engineering, right? So they have to use this. Not they have to, yeah, but they probably do use it. Okay. So the next thing is the following. If you take any 3 by 3 matrix, which is any n by n matrix, and in our case we are focusing on F, but any 3 by 3 matrix or n by n matrix will work. And this is theorem in mathematics, nothing to do with mechanics part either. So this can be written as the product of two matrices or two tensors, and this decomposition is not unique. So it can be written as R times U or V times R. Properties are that this R here is a rotation matrix, which means R inverse equals R transpose. So it's a rotation matrix, and then determinant of R is plus minus 1. And we will take it as to be plus 1 because we don't want to go from left-handed to right-handed and vice versa. The properties of U and V are U equal to U transpose, V equal to V transpose, and incidentally this V is not volume. Sorry for the notations, but I'm afraid I cannot get out of it because that's the way our life is, because of 26 alphabets. And this is again in most books, most papers, I should not even say books, this is the notation followed. Okay, so V equal to V, so U is symmetric, V is symmetric, and R is orthogonal. So if I take the determinant of both sides, so I will get determinant of R, which is plus 1 times determinant of U, and that will equal determinant of V times determinant of R. So it's clear that determinant of U equals J and determinant of V equals J. J is the Jacobian we talked about there. So J is not 0, J is positive. So these matrices, so these U and V, not only they are symmetric, but they are positive definite. I did not write positive as P-O-S-I-T-E-V, but I just wrote positive. So both U and V are symmetric and positive definite. So what can we take? What can we say about their eigenvalues? They are positive. Very good. So the eigenvalues of U and V are positive. So if and we defined C yesterday. So C was F transpose F, and if we do that, we will get U transpose R U, and that's U square, because R transpose R is identity. right? R transpose R is identity. Is it okay? Because see, when I take F transpose, it will be U transpose R transpose, and then R transpose R is identity. I did not write that, and so U transpose is U. U transpose is U. Therefore, U times U is U square. So, what can we say about the eigenvalues of U and eigenvectors of U? Eigenvalues of U are positive. Great. What about eigenvectors of U? Sorry. Let me rephrase my question. What is the relationship between the eigenvectors of U and eigenvectors of C? Same. Very good. So, eigenvectors of U and C are same. Eigenvalue of C is the square of the eigenvalue of U. So, if eigenvalue of C was stretch square, what can we say about the eigenvalue of U? It is stretch, right? So, now what about so let's introduce another tensor, and I will show you what is the mean, why are we doing it. It will come in a minute. Oh, sorry, a few minutes, not a minute, few minutes. Okay. So, let's say B. Yesterday we said no, C is a right Cauchy-Green tensor. The reason we call it right is because C equals U square. U appears to the right here. So, this result I wrote here, this is called polar decomposition theorem. So, this is polar decomposition of F. Because somebody might ask you, did Ramesh say anything about polar decomposition theorem? So, I am saying here that so this is polar decomposition theorem. So, F equal to R U equal to V R. Like in small deformations, we say the deformation equals translation, like infinitesimal translation plus infinitesimal rotation plus infinitesimal strains. But in large deformations, it is depending upon whether you use this or that. So, this one U, it causes stretch, change in angles as well as rotation, but this R only causes rotation. So, it is a U followed by R or R followed by V. See, like we wrote F1 followed by F2. So, if I now talk about B, so that will be making use of this V here. So, that is instead of its F transpose F, it is going to be F transpose. So, this you can say for the time being its definition. So, it is left Cauchy-Green tensor. So, this one is left Cauchy-Green tensor, and that one is now V R transpose V transpose, and that is V transpose, and that is V square. So, C is U square, B is V square. Now, what are the relationships between C and B? That is the next question. Okay, that is where I am headed now. What are the relationships between C and B? So if we look at this, so this one says V equals RU R transpose. Remember, R inverse is R transpose because R is orthogonal. So if I post multiply here by R transpose, so this R and R transpose will become 1. So that's what I got. Either you can solve for U or you can solve for V, whichever way you like, makes no difference. So this is V square. So this is R U R transpose, and then R U R transpose, because V square is V times V. So this R transpose R will become identity. So we get R U square R transpose, or this is R C R transpose. So B and C are related through this R. B and C, they are related through R. So what can we say about the eigenvalues of B and C? Eigenvalues, not eigenvectors, eigenvalues. What can we say about the eigenvalues of B and C? You can see that B equal to RC R transpose, or C equal to R transpose BR. Yes, very good. So eigenvalues of B and C are same. So eigenvalues of B are also squares of principal stretches. Eigenvalues of B are also squares of principal stretches. So if you want to find principal strains or principal stretches, you can work with either B or C. They are identical, exactly the same. So if somebody says, okay, find eigenvalues of, find principal strains, so you can either work with B or you can work with C. But the next question, that will make a difference between whether you should use B or C. Now I want to find directions along which strains are, along which stretches are maximum or minimum. So I want to find directions. So it depends whether you want to find directions here or you want to find directions here. Whether you want to find directions in the undeformed state or the deformed state. Yesterday we showed that if you wish to find principal directions or directions of principal stretches, they are eigenvectors of C. So they are, like we said, N1, N2 and N3. Okay, that's what we did, we said yesterday. So, and of course, now what will happen if I apply F to N1? So what should I get if I apply F to N1? Let's see how many of you remember what we did yesterday. I'm sorry? Yes, you are right. Thank you. So what I will get is the position of N1 in this configuration, in the deformed state. If you recall, yesterday we said P prime Q prime I was F I L P Q L. So if you apply F to a line element in the undeformed state, you get its deformed position, right? So you can replace PQ by this N. So what we will get is the deformed position of vector N1. Will it be a unit vector? there n1, n2, n3 are unit vectors. So, will f operating upon n1 be a unit vector? I think you want to say something. Speak up. Very good. Not necessarily, because f, if you look at f, which is RU or VR, U stretches and rotates and R only rotates. So, you are absolutely right, not necessarily. It is only when f is a pure rotation that the magnitude of this will again come out to be a unit vector. So, you are absolutely right. So, this gives us the position of deformed position of n1. So, let us see what happens then. So, I can write this as R U n1, because f equals RU. F equals RU, right? So, what about this time U times n1? So, what will this be equal to, this product? Now, remember n1 is an eigenvector of C. You already told me correctly that n1 is also an eigenvector of U, right? Because you said eigenvectors of U and C are same. So, n1 is an eigenvector of U. So, what should U n1 be equal to then? Pardon me? Eigenvalue. So, that should be, eigenvalue is say lambda 1. I think we denoted stretches by our eigenvalues of C by lambda square. I forgot whether we denoted by lambda square or lambda. So, if we denoted by lambda, then this will be square root. If we denoted by lambda square, then this is lambda. So, this is a square root of the eigenvalue of C, and eigenvalues of C were squares of principal stretches. So, this is principal stretch, and then this is n1. So, lambda 1 or n1, this is a unit vector because R is a pure rotation. So, R is a pure rotation. So, this one will be say lambda 1 times n1, where n1, n2 and n3 they are principal directions of principal stretches in the deformed state. So, they are directions of principal stretches in the deformed state. So, if you want to find after I pull my skin which directions have the maximum stretches, you work with, you need to find this. Okay, so, you need to find this one, and this one is R times n1. So, let us go back to this relation. We have R C R transpose. So, we have C equal to, I am trying to see, so let us say C equals R transpose B R. What I want to show you now is that this n1 is also an eigenvector of B. this n1 we are talking about there, we found there is an eigenvector of B, and so that is really R times n1. So let's see what. So C I'm trying to think of what's an easy way for me to show you that okay. So let's go back here. So we have Fn1 equal to all of that stuff. So what I have is then Fn1 equal to V R n1, and then we have this equal to V n1. Is it okay? Because we wrote R operating upon n1 is this one, so that's what I wrote there. So this thing is F n1 is lambda 1 n1. All I'm really doing now is I have substituted, instead of F equal to RU, I have written VR. Please, are these steps okay? If they are, we are almost done. So now look at this one and that one. Look at the first one and the last one. These are all equal signs, right? So I can erase the middle part. So what does that tell us? That little n1 is an eigenvector of V. Little n1 is an eigenvector of V, and the corresponding eigenvalue is lambda 1. Lambda 1 also was an eigenvalue of U. So U and V have the same eigenvalues, not the same eigenvectors, but the same eigenvalues. Eigenvector of U is a principal stretch in the undeformed state. Eigenvector of V is a principal direction in the deformed state. So if you want to find in the deformed state, you work with V, and if you want to find in the undeformed state, you work with U. Now we are home. C is U square. So if you work with U, is the same thing as you are working with C. The only difference is you will get the square of stretch. What about here? B is V square, right? So if you find, what can we say about the eigenvectors of V and B? They are same. So if you want to find principal directions, which means directions along which the stretches are maximum or minimum, in the reference configuration you work with C. In the current configuration you work with B, because B is square of V. V and B have the same eigenvectors, but their eigenvalues are like squares of, well, eigenvalue of B is square of the eigenvalue of V. So does it make sense? So why we have introduced B? That's one motivation, but there is another one too that will come up now. Okay, I will give you one more motivation for B. Okay, so this B is called left Cauchy-Green tensor. left because this B is derived from V. V appears to the left of R in the polar decomposition theorem. So, that is how this left and right come up into picture. So, one is left Cauchy-Green tensor and the other is right Cauchy-Green tensor. Both are equally good, both give you principal stretches, like their eigenvalues give you principal stretches, their eigenvectors give you principal directions. For C they are in the undeformed state, for B they are in the deformed state. We will need both as we go along when we talk about material models for rubber. We have not done that, or any soft tissue. When I say rubber, is if you rubber like materials, our soft tissue is also modeled as a rubber like material. I mean, like if you take either my skin, or if you supposing cut and take a soft tissue inside, that is also modeled as a rubber like material. Our bladder, same rubber like material. So, it's many arteries rubber like material. The only difference is the elastic, the moduli, I cannot use the word elastic constants, the moduli, they are equivalent to say Young's modulus is different for this skin, is different for the soft tissue, is different for the bladder. How many times does our bladder expand and contract? Okay, tell me, how many of you can guess how many times does our heart beat in our lifetime, average lifetime, not because none of us knows how long we will live, but let us assume a person lives for say 70 years. So, can you guess how many times does our heart beat? Is something like 10 to the power 12, 2 or 3 times 10 to the power 12 cycles. Of course, they are wondering how did I come up with that number. Okay, what is the average heartbeat? I am sorry, 70 per minute per sec, 70 per minute. But if you want to slow down, then go and jog, then it will become less. So, let us take 70, right. So, it's 70 cycles per minute, and there are 60 minutes per hour. There are 24 hours per day. There are 365 days per year, and multiply by 70 years, right. So, that is how many cycles. If we had our tires made of this same material as our rubber, you will not have to, not only you, your children and probably grandchildren will not need to replace the tires. Count this. This is, I think this comes out to be something like 3 times 10 to the power 12. 1, 2, 3, 4, 5, 6, and then we have to multiply up. Anyway, it comes a huge large number. And none of the tires on our cars, they go through that many cycles. So, let's look at nature. It has optimized the material of the heart tissue. The one thing, of course, which we do not have for tires or other man-made materials is regeneration. See, our cells die and then new cells are formed. So, they really keep on refurnishing the heart muscles and heart tissue. And same thing is for every other part of the body too, not only the heart, but most of us pay more attention to the heart than to other things, because if it stops beating, then if it stops beating for a minute or two, we are gone or severely damaged. So see, you can see that, and there is a large deformation involved too. I mean, the heart muscle is not that the heart muscle is undergoing small strains, infinitesimal strains. No, it's not true. Okay, I mean, it's certainly not true. And well, okay. Now, so I'm going to erase this unless you have a question. I'm going to show you why, what is another reason for B, or talking about B, and then we will have a coffee break or tea break. So yesterday we talked about finding ds square over capital DS square, right? That's how we said this -1. When we subtract -1, then we talked about E, the Green Lagrange strain tensor. Now let's say I want to do things differently. I want to work in this configuration. So if I work or take x, capital X, and time as independent variables, and that's typically what we do in solid mechanics. I said typically, I did not say we have to do it. Then the description of motion is called Lagrangian. Is called either Lagrangian, referential, or material. You will see these three names used in the literature. Referential, we are taking reference, these are the coordinates of a point in the reference configuration. So that's clear, right? Material, we assigned these coordinates to a material particle which never die. So material word is okay. Lagrangian, according to Trussell, Lagrange did not give this. He did not use it, but most engineers call it Lagrangian. So you will see these words used, Lagrangian, referential, material. In fluid mechanics, it's very hard to find from where the particle came. So it's very hard to find out its reference configuration. So we work in terms of little x and time. So we know the fluid is here. So we want to see what's happening to the fluid particle that I'm seeing now. Here I say what is happening to the material particle Ramesh, because that's the name given to it. But in this case, now I'm saying whoever is here, I want to see its velocity, I want to see its temperature. Here I say no, I want to follow this particular person all the time. So if you take these as independent variables, I'm not writing this part. Then the description is called Eulerian or spatial. So, Eulerian again is Euler after Euler. Spatial is you are looking at space particles now. So, it is descriptive, like you are looking at what is happening in space right in front of your eyes at this moment. These two are related, and for us we said like yesterday that xi, and as I said before, we are sloppy. So, this is a function and that is a value of the function. So, these are three equations. This condition j greater than 0 implies that I can solve these three equations I can find the inverse. So, these three equations can be inverted. So, this is implicit function theorem in mathematics. So, if the Jacobian is not 0, then you can solve this, you can invert these three equations. Actually, even if Jacobian is 0, you can invert them, but the inverse may not be differentiable. The inverse, yeah, that is the, and since we want the inverse to be differentiable, so we require that Jacobian is not 0. Okay. So, it's now if we supposing now I have a temperature, theta is temperature. So, if I have temperature given as a function of big X and time, where I am headed is the non-linearity shown to you yesterday for the fluid mechanics part. I have shown you non-linearity, one non-linearity for the solid mechanics part, strain tensor in terms of displacements. So, in fluid mechanics, the acceleration itself introduces non-linearity, and that is where I am headed. Before, then I will talk about B. I did not forget that I have to talk about B. For B also I need to invert this, and so for temperature also now I am inverting it. So, if I am given temperature as a function of big X and time, to get this, what one needs to do is, to each particle here one needs to glue a thermometer. Okay. So, to each particle you glue a thermometer, it is permanently attached to it, and then you can watch its temperature as things evolve. In this case, if I want to express as a function of little x and time, then I do not have to glue thermometers there, but I have thermometers in space here, and as the particles move by, I measure their temperature. So, in this case I am measuring the temperature of different particles. In this case I am measuring the temperature of the same particle. So, you see the difference between the two. Okay. But mathematically now, since XL can be expressed like this. So, I get that. Is it okay? And then you can simplify this, and this becomes a different function of little xi and time. Because once you have substitute for big X in terms of little x, then you forget about, then this becomes a function of little x and time. Is it okay? So, this is Lagrangian description or material description, this is spatial description. Now, I want to find the rate of change of temperature of one particle, say Ramesh. So, if I want to find the rate of rate of change of temperature. This is rate of change of temperature with, let me say, d theta over dt, or partial derivative you can say this is xl fixed. And normally we denote time derivative by putting a superimposed dot. And if you are keeping particle fixed, then this is called total derivative. So, this is a total derivative rather than partial derivative, you will see in a minute. Now, I have this mathematical relation. So, this one is easy because to find this, all I have thermometers glued to me, glued to every particle. So, you know its temperature at different times, you can find the rate of change of temperature. Fine. But in this picture, you don't have you have temperatures sitting in space. So, whatever particle passes by, you take its temperature. So, at different times you are taking temperatures of different particles that happen to be there. Does it make sense? And that is embedded in the fact that this little xi is really a function of big X and time, because little xi is a function of big X and time. I have to keep big X fixed, not little x fixed. So, time comes twice. Time is here in this one and time is here. So, I am taking no total derivative. So, if I find, so first time I differentiate with respect to xi, and then I differentiate xi with respect to this plus delta theta hat over delta t, and this one is little xi is fixed. So, time appeared twice. So, I am differentiating first, well, I have to differentiate with respect to time twice now, this one, and time is in this implicitly included here. So, that's how we get this expression. So, what is this quantity? Delta xi over delta t. What is this called? Very good. So, it's the rate of change of position, right? So, it's the rate of change of position of a particle. So, that's velocity. And let's say, so Vi is delta xi over delta t, keeping big X fixed, and that's velocity. So, I can replace this one by this. This is Vi. You told me correctly, it's velocity, right? So, this becomes convective part of temperature change, and this is instantaneous part of temperature change. This is convective part of temperature change. This is instantaneous part of temperature change. Is it okay? So, what is rate of change of velocity? Rate of change of velocity keeping big X fixed, acceleration. So, if I want to find acceleration, so that's rate of change of velocity keeping big X fixed. I'm almost done. I'm sorry, I'm keeping you away from the coffee break, but just I just have to say one more minute. So, now I take my theta equal to say V1, because theta was a scalar quantity, right? So I'm now taking one component of velocity, so that becomes a, then I will take second component of velocity, and then I will take third component of velocity. So if I take one first component, I will get delta V1, oh sorry, delta V1 over delta T. Oh. No. So if I take first component of velocity, so V1 dot, that's you told me is acceleration. So that will be A1 will equal delta V1 over delta xi Vi plus delta V1 over delta T. Replace theta by V1. Does it make sense? I mean, it was easier for me to motivate rate of change of temperature, but now I can replace temperature by one component of velocity, and then I will do the same for the second component. So A2 equals delta V2 over delta xi Vi plus delta V2 over delta T. And yesterday when you saw, this was the local part of acceleration, this is the convective part of acceleration, and when we write this in terms of a vector, like you write all three equations in one. So you have A, which is a vector, equals delta V. Actually, Professor Gu has used U for velocity, I am using V for velocity, plus this term is gradient of V. So that really gives you 3 by 3 matrix, because you have here V1 over xi, you have three components, V2 over xi, then you will have V3 over xi. So you will have, so this is really a 3 by 3 matrix, and then it operates on a vector, and so you can write this as dotted with V. But we have to be careful, we have to understand what dot really means. But if you don't like that, I mean, I personally don't use it, I use index notation, then I am not in trouble. I mean, it's very clear to me what I am dotting there. So if I were, what I prefer to do is I say Aj, Vj, Vj, and that gives me three equations. This is the same as this equation. So the nonlinearity in fluid mechanics, because they use spatial description, not only they, I mean, it's easier to use spatial description. I mean, I did not mean to say any negative thing. In fluid mechanics, all of us, including myself, I use spatial description, Eulerian description. And in the Eulerian description, acceleration is always a nonlinear function of velocity. Okay. In the Eulerian description or spatial description, acceleration is always, the convective part of acceleration introduces the nonlinearity. Whereas in solid mechanics, the strain displacement relations and stress strain relations both introduce nonlinearity. In fluid mechanics, we usually use Navier-Stokes equations. We make the assumption that the stress tensor is directly proportional to, roughly speaking, is proportional to the strain rate tensor. I have not talked about strain rate yet, but I will. So there, the major source of nonlinearity besides turbulence, which I did not say anything yet, probably I won't say anything. Actually, I will not say anything about turbulence, because I don't know, I have zero knowledge of turbulence. So in fluid mechanics, major sources of nonlinearity are this one and then turbulence part. In solid mechanics is the strain displacement relations and then the stress strain relations. Okay, so I think now we can have break. Then I will talk about B, which I have not said anything yet. I will. No. Okay, thank you. So I think we, even though I'm already late, so so I'm 15 minutes late because I'm supposed to go up to 10:50 according to this stuff. So we can resume. You will get the temperature of XL. The only difference is, in one case you are plugging in, you are substituting say Ramesh here. Here you are substituting where I am at time t, but you are still finding the temperature of Ramesh. This function of course will look different from this one because you have substituted for uppercase x in terms of lowercase x. So the functions look different, but if you plug in the present position of particle XL, you will get the temperature of particle XL. So same thing here. If you plug in the velocity of particle XL, you will get acceleration of particle XL. Accelerations, velocities and temperatures or anything else, these are really defined for of material particles. So if you say the temperature here in space is say 50 degrees, it's really the temperature of the material particle that happens to occupy that place at this time. When we go to a doctor or physician, they put thermometer in our mouth. So what they are really doing is trying to get temperature of my temperature, right? Assuming that the temperature of my tongue is the same as the temperature of the rest of my body. Nowadays, if you go to the airports, especially in China, in Beijing, they have a thermometer that's not touching you. So they, as the passengers or visitors come through the immigration, they take the temperature of everybody, and if the temperature is abnormal, they put the person, they don't let him or her go. It's quarantined because they don't want to spread. Well, anyway, all countries basically they don't want to bring in sick people. But I have not seen that radiative thermometer anywhere else at an airport except in Beijing, and especially when there was that Zika virus fear, they were taking temperature of everybody. You don't know it, but as soon as you walk through, but these days, even in physician's office, they don't put thermometer in your mouth, they do like this now, so they can take temperature without touching you. So the point is, this is strict mathematical relation. Even though functional forms look different, but the values are exactly the same. Since this is a function of little x, so you really are, if you just differentiate with respect to time t, you are not getting the temperature of the material particle that happens to be there. You are getting the temperature variation of different particles, because different particles happen to occupy the same place at different times. I think many of you drive. So in this country, in India, I don't know how many of you get, like what is the challan rate or ticket rate, but in the USA it's very strict, roughly speaking strict. So if the speed limit is 100 kilometers an hour, they don't quote me, but they don't give us a challan if we go up to 110. Roughly 10 kilometers you can go above, roughly. But if you go 11, they will give you a ticket, which means challan. So you have to pay fine, and fine is heavy. It's not trivial. So but the story is the policeman is really not taking the speed or not measuring the speed because he's not following you. So if the police person is here, he is measuring the speed of the car that happens to be here. To measure the speed of this car at different times, he has to follow the car, but they don't follow. Well, sometimes they do follow, but of course they have infrared, or they have a radar, and then they can track you. Even if they can track you from a distance, they focus radar on you and see, okay, for 1 minute how fast or how slow you were driving. So if you want to find the rate of change of temperature of a particle, you have to follow that particle. But in this description, in the spatial description, we do not follow a particle. We are sitting at a place, like the police person is sitting there, and then they keep on watching different cars go by. Better example might be fishing. If you go for fishing, you are stationed there, and river is flowing, fishes are flowing by. So if you want to follow the temperature of a fish, then you really have to track that fish, which we don't do. And then if you use this description, then you have to take convective part and the local part. Okay. So now I think I said in the beginning that I will give you another reason why we introduced B besides finding eigenvectors and eigenvalues and positions in the reference and present configurations. So now let's take so we said yesterday that P prime Q prime is FIL evaluated at point P times PQL. So where this is PQ and this is P prime Q prime. So let me put double primes here. So in this figure. So now if Jacobian is a positive, actually it's not 0, we can invert this and write PQL equals F inverse Li P double prime Q double prime I. So this is a 3 by 1 vector, this is 3 by 1, this is 3 by 3, so I'm inverting it. And so what is now ds square, little ds square? So that's P double prime Q double prime I, P double prime Q double prime I. So it's F inverse Li PQL. And then we have two of those, so I need to write F prime Mi PQM. PQ is F inverse P prime Q prime. I think you did not like it, so that's why I'm going over again. So ds square is the inner product of this vector. So this term is for this one, and this one, the other term is for the second one. Yes?
I'm missing something. P dash Q dash or double prime
Yeah.
is equal to F times PQ. It's not F inverse.
You are right. I goofed. Sorry. You are right. Sorry. I goofed. Yeah. It's my mistake. Yeah. I goofed. Yes. You are right. I had made a mistake. So it's PQL, PQL. Actually, haste makes waste. That's what I was trying to do. And it's no excuse. It was my mistake. Okay. So it's PQL, PQL. And that's F inverse Li P prime double prime Q double prime I, F inverse Lj P double prime Q double prime J. No, I think it's okay. So what about this quantity? But I think it's not quite clear what is this equal to. So we wrote B is F transpose. That's how we defined B, right? So let's see in terms of indices then. So this is Bij is Fil Fjl. Is F transpose. So when you will take the transpose of this, you will get Lj. Then L and L will be next to each other, and that's multiplication. Is it okay? So now if I take B inverse, so that is going to be F inverse transpose F inverse. Because when you take the when you invert the product of two matrices, then is then you have to change the reverse the order of multiplication, and then the inverse of the transpose is the transpose of the inverse. And I mentioned yesterday we will need some matrix multiplication, but this is elementary stuff which you have learned. So if I write this in terms of indices, so it will be B inverse Ij is going to be F inverse Li F inverse Lj. Again, because this is transpose, so I will have to interchange the indices. Is it okay? Because we are almost there now. We are there to get to the interpretation for B now. So this is B inverse Ij P double prime Q double prime I P double prime Q double prime J. So see, so B shows up. So yesterday we talked about C, now it's B. And if I divide by little ds square and then subtract 1, or I forgot, well, let me see, we will see it. Yeah. So it's 1 minus x. So we will get delta Ij P double prime Q double prime I P double prime Q double prime J minus wait, let me do it. D little s square. So this term is 1 and then minus B inverse I j So, now we are finding, roughly speaking, change in length per unit final length. Yesterday we had change in length per unit initial length. Both are strains, but in one case you are finding change in length per unit initial length. When I realize we have squares here. But yesterday we had change in length per unit undeformed length. Both gives you change in length per unit length. So, the difference is, in one case your extensometer is fixed, like when you did experiments in tension in your undergraduate class. So, we have a bar and then you put an extensometer here. So, you measure the gauge length, which is delta L, or sorry, which is L, because we call it L, and then delta we are going to use it for the elongation. So, that is the gauge length. Then you apply loads and you keep on measuring the displacement or elongation on this with this extensometer. Then you find delta L over L. So, that gives you change in length per unit undeformed length. On the other hand, now if you find delta L over little l, which means little l is the current gauge length. So, little l will keep on changing as you keep on deforming. So, some people call this as true strain. There is no false strain. So, don't confuse between true and false. There is no false strain, but some people call this as true strain and this is nominal strain. So, yesterday what we did was something like this. Today what we are doing is something like this. I said something because in the way we are doing it is really, this is not this is final length. So, this is L plus delta L, and I will give you one more definition of strain. There are, as I said earlier, there are many definitions of strains. So, okay. So, now is the difference between the two strains clear? Yesterday we used C, today we are using B inverse, and if we so this we can write it as, say, delta I j minus B inverse I j P double prime Q double prime I P double prime Q double prime j over ds square. Okay, these are common factors, so I just took it out. So, this quantity that I have in the this one, yesterday we had C minus 1, right? Now we have 1 minus B inverse, and oh sorry, so this thing is Also it has a name, and so this we will call it, say, twice epsilon ij. Again, I am not dividing by 2, but so this is defined as delta ij minus B inverse ij, and this is called Almansi Hamel-Strain tensor. In some books you might see the word Eulerian strain tensor, but I am following Trussell's terminology. So you might see in some books the one we talked about E yesterday as Lagrangian strain tensor, and this one as Eulerian strain tensor. Now, if you work in terms of displacement gradients or displacements, this thing comes out to be equal to delta ui over delta xj plus delta uj over delta xi minus delta uk over delta xi delta uk. And this, yesterday I showed you the derivation of E in terms of displacement gradients, but today I am skipping that part. So the difference between what we did yesterday, first of all, yesterday this was a plus sign, today is a minus sign. It's correct, okay, it's a minus sign. I didn't cook it up. You do algebra, that's what you will get, minus sign. Yesterday these derivatives were with respect to big X. So we were expressing u as a function of big X and time. Now they are functions of little x and time. There is still nonlinearity. This term is nonlinear in displacement gradients. The only difference is yesterday displacement gradients were with respect to big X, today they are with respect to little x. So in solid mechanics we usually take big X and time as the independent variables. In fluid mechanics we take little x and time as independent variables, but the two are related with each other. So when you do the fluid structure interaction problem, like blood flow in our arteries, then you have to be careful, because if in fluid mechanics you are using spatial description, current description, and in solid mechanics you are using now, say, Lagrangian description. When you want to do the interaction between the two, you have to be careful. Okay. So that's why some codes they say we are going to use ALE, arbitrary Lagrangian Eulerian formulation. So that's what makes fluid structure interaction problems more challenging. Well, one reason they are more challenging is that you have to track which fluid particle or which solid particle is where, which at the present location, and when you want to find the pressure, and there should be no interpenetration, which means one material should not penetrate into the other one, because obviously, right, that's a physical condition. And many softwares, commercial softwares, they have difficulty, serious difficulty in satisfying this non-interpenetration condition. It's a non-trivial task, especially if you do a three-dimensional problem and your structure is deforming. So one version of a commercial code like LS Dyna was allowing the fluid, which water, to interpenetrate into a rigid body, because the technique being used to enforce the non-interpenetration condition was not good enough. That's all one can say, it was not good enough. I think the present version they have improved, but because if you assume the fluid, which is water say, to be inviscid, non-viscous, then it can slide. There is no continuity of the fluid is not sticking with the walls. So, the velocity is not continuous, only normal component of velocity has to be continuous, and that creates problems because you have to account for the sliding. Okay. So, this gives you one more reason to talk about B, that if you are using present description or you are expressing displacements in terms of current coordinates, then you generally work in terms of epsilon or in terms of B, and you will see B and C will actually B will play a big role when we talk about material models like constitutive relations. Okay, now let me say a few more words about I just said delta L over L, so I will say a few more words about that, and then maybe talk about strain rate part in the afternoon. Any question you have about this stuff before I erase it?
The difference between considering the Lagrangian description and the Eulerian description for Weierstrass interaction problems. So, can we kind of bypass it if we use small deformations?
Yes. See, yes. Yes, but if you use small deformation, it's okay. If your submarine is made of steel, it's fine.
You can't address interesting problems.
Yes, you can. You cannot say I have a torpedo. You cannot say my boat is made of something flexible, or a folding material, say, or a collapsing material. Or supposing I want to dive, then you can dive only up to a few meters, because once if you want to go up 1 kilometer deep into the sea, then depending upon what suit you are wearing, the deformations may or may not be small. Okay, so if you want a physician like a surgeon to operate on you based on small deformation theory, good luck. You are always praying. I mean, you are praying anyway all the time, but if you are based on whatever he is putting in our body is based on the design using small deformation theory, it can create problems. I am not saying it does not work, but because they have tested millions of times, so they have made corrections on the way. So it all depends upon the problem one wishes to solve. Like my parachute. So it depends upon where I inflate my parachute. So if you use a large deformation theory, nonlinear theories, you can still do small deformation problems, but the converse is not true. The price paid is because you are using nonlinear theory, so it takes more computational time. And as I showed you one example yesterday, the nonlinear problems do not necessarily have a unique solution. Because yesterday I showed you that half sphere, and let's look at this problem, which again I think Professor Gay also mentioned yesterday, this flow between two cylinders, or like there is called Couette flow. So you take a cylinder, this is it's a hollow cylinder, and so it's a hollow cylinder. Now you put a rigid rod, it's a rigid cylinder or rod or whatever you like. between these two he had viscous fluid, right. Let us put rubber. It's very, or dough with which we make chapatis. The reason I am saying dough or rubber is because they are soft materials, otherwise you really will have to work very hard. So, let us put soft material, and I do not know whether you have heard of super glue or not. So, let us put super glue here. It is not oil, it is super glue, permanently glued, and usually super glue, unless you even if you have an elephant pulling the plate, two plates glued with super glue, even an elephant cannot separate them apart. So, for our purposes this super glue will not let these two surfaces separate. So, I put super glue. Okay. So far together we are okay. Now, keep the outer cylinder fixed, like hold it. Rotate this one through 2 pi, completes a round circle. So, what is the final displacements of particles on the boundary? 0, because they have come back to the initial position. So, the displacements of these particles is 0. Displacements of all particles on the boundaries are 0, right. Does it make sense? Now, I want to solve the problem either numerically or analytically. So, should not I get two solutions, one with 0, one where there are displacements inside are all zeros, and the other one where displacements inside God knows what they are, because all we know is on the outer boundaries displacements are 0. And I said 2, actually you should get infinitely many, because it is not only 2 pi, it is 2 pi times the number of any integer number. See, if my nonlinear theory is good, this problem should give me many solutions. So, that is the difficulty Professor Ghia was also mentioning yesterday. He was more focused on, well, because of his interests he was more on fluid side, because of my interest I am more on the solid side. But in fluid mechanics another thing that comes up is, if you do not use Newtonian fluid, Newtonian means viscous stress component is proportional to the strain rate. If you use non-Newtonian fluids, and like many oils are non-Newtonian fluids, then, and if you fill it up only say up to here, not all the way, but only up to here, for Newtonian fluids this surface basically stays flat, the free surface stays flat, but for non-Newtonian fluids you get curvature here. Whether the curvature is this way or this way depends upon the viscosity of the fluid. So, there are many interesting effects that show up in nonlinear problems that we do not see in linear problems. Give you another example. I know I am diverting from my stuff. Most of you have done torsion test, right? You take a cylinder and you apply torque. So, if you take a cylinder, whether it is solid or hollow makes no difference, the only thing is it's made of a material that you can twist easily, otherwise you have to have a strong machine. So, you fix this upper end, typically we do that, apply torque here. So, if you do linear theory, small deformation theory, then this length L does not change. There is no change in length when you do pure torsion. Now, if you do nonlinear theory, and this end is obviously you are not you are allowing it to move up and down, the length will change. And this is not new. In 1878, which is like long time ago, 140 years ago, when we did not have these sophisticated instruments to measure things. So what did he do? This is the name of the person, Poynting. I think yesterday we were talking about innovative stuff, right? So Poynting, he took a very long wire, hung it on a tree limb. So the wire is not like 1 centimeter we use these days or 1 millimeter we use these days, and he put a mirror here to reflect light. When he twisted, the wire elongated. Depending upon the material. So when I say elongated, it could be contracted also. So there is a change in length, and you will say, hey, how can that happen? The nonlinear theory predicts that. I wish I had time to show you the analytical expression, but I don't know we will, even because we have only 6 days, one is gone, so or 1.5 is gone with my stories. So this Poynting, like he observed this in 1878 and it's called Poynting effect. So it's a coupling between elongation and twisting, which you don't get if you use linear theory. So there are many interesting aspects of nonlinear theories, and these are real. This is not bogus stuff. I mean, he observed it, so it's not that I'm cooking it up. Another example I can give you, which let me give you, since I said I will give you, so I will give you.
The Poynting effect holds even for materially linear
That's an interesting question. I'm thinking, so long as I think you account for geometric nonlinearities, which means nonlinear strain displacement relations, most likely yes, it holds. That means stress is a linear function of strain. That's what you meant, right? And the effect is proportional to the square of the angle of twist. So that's why you don't see in the linear theory, because in linear theory you neglect quadratic terms, and that's why you don't see it. But most likely the answer is yes. But the next one I'm going to show you does not hold for a materially nonlinear equation. So you need both material and geometric nonlinearities. The next one I'm going to show you, not show you, but discuss or describe. Obviously, I'm not showing you anything, but you are taking my words for it. These are not, I'm not cooking up anything, so don't. Take a membrane, and this is again made of soft rubber. So membrane is thickness is much smaller than the length. Roughly balloons, like and this is the experiment we did. My colleagues did, I did not do it. So it's a balloon that we use at children's party, we blow them up, or at marriages also. So it's that kind of balloon, soft rubber. And if you cycle it a few times, like blow it and then blow the air out and then blow it again, is to get rid of some initial Moulin effect. Otherwise, it shows you the elasticities keep on changing depending upon how many times you blow it. So if you do it few times, then it stabilizes. So, the key is the following: the loads you apply, they are dead loads, which means their direction and does not change. So, you take a bucket. So, these are strings attached to the sides of the membrane. Membrane is made of an isotropic material, and you hang those strings over a pulley. So, you do it on this side as well as you do it on this side, and this side. This is made of an isotropic homogeneous material. So, could be our bladder. Before you do the experiment, you draw a grid. And even though mine does not probably show you, so all these are all squares. So, you draw a grid, and this grid is made of squares. So, if you have say 10 centimeter here, 10 centimeter here, and then you can have 1 centimeter separation. So, you have 1 centimeter by 1 centimeter square. So, you draw a grid. These are, you apply equal loads on both sides. All four sides have the same equal and opposite. Well, these two have equal and opposite load, these two have equal and opposite loads. So, system is in equilibrium. It is a static problem. So, what do you think, what kind of deformation should I expect? It is an isotropic homogeneous material. You are applying dead loads, equal dead loads on both sides. So, should a square, what should be the deformed shape of a square? Is my question making sense? So, I took a square membrane made of an isotropic homogeneous elastic material, and the example I gave you is a balloon, that balloon, rubber balloon, and we are applying equal and opposite dead loads on the sides. So, what should a square deform into? I am sorry? A square should deform into a rectangle. Why? It's an isotropic material. And also we assume this rubber is made of an incompressible material, which I will define in a minute. What is incompressible? So, the normal expectation is that a square will be deformed into a square. So, as you keep on, that's what happens initially. So, you keep on gradually increasing the load. Now, remember, you have to increase the load on all four sides. So, you can have either water drip, or you put a stone. You control so that the system does not get out of equilibrium, right? Otherwise, you are introducing some kind of non-homogeneity. Depending upon the material constants, at a certain value of this load, a square switches into a rectangle. When I said like certain value, that value depends upon the material of the rubber. I cannot say that you take balloons made from one company or balloons made from a different company, or you have a soft rubber. The reason I am using soft is because you can easily deform it. But as far as we are concerned, as far as the theory is concerned, all we really need is a incompressible rubber material, rubber-like material. So, if you give me the material parameters, I can tell you at what value of the stretch this will switch. So, initially stretches in both directions are same, like if it is say 1 centimeter became 1.1 centimeter, it became 1.1 centimeter along x axis and 1.1 along y axis. So, if this length was 10 centimeter, it became say 11 and by 11. After some time, it switches. A rectangle, sorry, a square becomes a rectangle. When it switches, I cannot tell you, unless you give me the material constants, I cannot tell you beforehand. So, this one is relatively speaking newer. I think this, and also beauty of this thing is Kearsley, he studied this problem and proved theoretically or analytically that this should happen, and he gave you the value of the stretch at which this will happen.
Some form of instability.
Yes, of course, yes, it's an instability, right.
And does it happen for linear elastic material?
No,
It doesn't.
no. First of all, you cannot have even stretch of like say 2 or 3 for a linear elastic material. No, linear elastic material will not, linear elasticity theory, even if you use it for a stretch of 2 or 3, no, it will not predict that. No, it's only a nonlinear theory predicts it. And then, so Kearsley, to make my story, he predicted this analytically, and he, I am trying to remember whether he wrote it or not, but some people attributed this to Treloar's instability. Treloar's, he did experiments roughly in 1940 or 50, this is like World War II. At that time there was a lot of interest in rubber like materials. That's how the nonlinear elasticity theory really flourished, because tires, there was a lot of interest in tires, and when especially airplane tires. So, he tested rubbers. He did this experiment, the one I am just showing you here, and he showed that stretches along x and y axis were coming out to be different. But he said they are different because of the anisotropy induced in the rubber, because of the aging, whatever reason, inhomogeneity, or he did not attribute to an instability. Actually, he said this is because of experimental errors or inhomogeneity or anisotropy. So, after what I am going to do is, since loads are same, I am going to average lambda x plus lambda y over 2 and plot t versus like the traction versus average stretch. But some people said because he observed different stretches, so that means he observed instability. But if you read his book or his paper, nowhere he mentions the word instability. He attributes this to more or less experimental errors. Also, the loads he used, that's a critical point. The loads he used, and therefore the stretches he got, they are way below when the instability occurs, when the analytically predicted instability occurs. So, this is an example of a theory predicting a phenomena that has not been observed experimentally. So, many times we try to develop a theory to verify something that has been observed experimentally. Okay. Or we develop a theory quote unquote to fit what we have seen in experiments. I should not use the word fit, but that's many times people use that word. So, they develop a theory to verify something that has been observed experimentally. However, this one predicts something that had not been observed experimentally. And I think one of you asked me if my material model is linear, will it predict the elongation or contraction in the torsion test. In this case, one can show analytically that a linear stress strain law, even if it is not, even if you use nonlinear description of strains, will not predict it. So, linear one is usually called Mooney material. Mooney is the name of a person, so it is called a Mooney material. Mooney material will not predict this instability. However, if you use a nonlinear stress strain law, that most often used in Mooney-Rivlin, Rivlin is another name, is the name of a person, that material model predicts it. Not only it predicts it qualitatively, it predicts it quantitatively. So, the rubber balloon, this balloon example I was giving you, it does obey Mooney-Rivlin material. And if you do analytically, you find out that okay, the instability should occur at a stretch of 3.2. So, it is 1 centimeter becoming 3.2 centimeters. And this is a long, this is a lot of strain. When I show you this, like 1 centimeter becoming 3.2 centimeters. So, we are not talking about small strains. And indeed, if you do experiments with that rubber, no, at a stretch of 3.2, squares, all of these were initially squares, they become rectangles.
So, has someone, for example, taken this very material, taken a circular shape and uniformly loaded it and seen that it transforms into an ellipse?
The answer is no, I have not seen that one yet. No, I have not. See, problem is, well, I should not cook up any excuse, because first of all, making a sphere, right, I have to put air in it to expand it.
No, just a circle.
Oh, circle.
Yeah.
Oh, and then you take a circular membrane, will become an ellipse.
Yeah.
No, I am not seeing the result, but chances are it should become, because it's really, it's not a new phenomena, except we are changing the shape of the body, right. So, its instability will be predicted, but I have not changed the shape of the body, because it's a new different shape, but fundamentally things won't change. But the answer to your question is no, I have not seen it, but I think we can do it. No, it should not take more than a couple of hours to do the problem. There is no guarantee it will be published, but okay. So, the motivation for using present length in the denominator, that's how this whole thing started, is the following. So, if we like in the simple tension test, if we define strain, axial strain, as change in length over present length, now I have changed dl, differential rather than delta L. So, this is axial strain or incremental axial, this is d epsilon. So, epsilon will become, you integrate this from the initial length to the final length, right. So, integral of dl over L is log of L, So, this will become log f over L0, because it will be log of f minus log of 0, and that means log of final length over initial length. Now, a beauty of this thing is, even though we are not talking about small strains now, we never said anything about that the final length has to be very close to the initial length. This thing is additive. Additive means in the following sense. So, my epsilon f is, or epsilon log phi, epsilon is log of f over log of 0, log of f over 0 I did not change anything. So, this is log of A times B, and that equals log of L f over L 0, sorry, L intermediate, then log of L intermediate over L 0. I think log of A B is log of A plus log of B. So, we can say now this is, say, epsilon 1 plus epsilon 2. So, these logarithmic strains, even though they are large, they are still additive. So, this I gave you the example in one dimensional case. So, in plasticity, those of you who may or may not work, may decide to work in plasticity, this is the strain definition often used, logarithmic strain. Now, the question is, how do I define logarithmic strain for a 3-dimensional problem? Sometimes this is called Hanke's strain. So, we are getting there. So, the question is, how do I define this for a 3-dimensional problem? For 1 dimension, it looks beautiful, right? It is very easy. Take the final length and divide by the initial length, take its logarithm, you got the value. Now, for a 3-dimensional problem, this is a little bit more work. So, can I erase this part and well, I will start here and then. So, for a 3-dimensional problem, so we have f equal to R u equal to V R, that polar decomposition theorem we talked about. So, either you can work with u or you can work with V, it does not matter. So, you work with, say, u, first find its eigenvalues and eigenvectors, and the third one, so if we find eigenvalues and eigenvectors, then we can write u as lambda 1, say u L m as n 1 L n 1 m plus lambda 2 n L 2 n m 2 plus lambda 3 n L 3 I wrote n L 3 n m 3. So, in component form, this is what Is it okay? Do you agree with this? It's the same matrix. All we have, now we are writing in terms of the eigenvectors. It still has, like, it's symmetric, so it still has 6 components. So the logarithmic strain is defined as log of lambda 1 times NL1 NM1 plus log of lambda 2 NL2 NM2. So now it really requires you to first finding the eigenvalues and eigenvectors, and then you can find U. And many softwares, including Abacus, they use logarithmic strain. This one is not necessarily additive, which means like if you have F1 then F2, and you have U1 and U2, you cannot get this relation need not hold, because U1 and U2 won't have the same eigenvalues, same eigenvectors. Okay, so this addition part epsilon 1 plus epsilon 2 equals epsilon will not hold for a 3-dimensional problem. When I say will not, I mean you may cook up a special situation in which it holds. Like you have supposing a simple tension test, and then you stretched it to up, say you started with 10 centimeter, you stretch to 11, and then you stretch to 12. That's not 3-dimensional problem, that's a 1-dimensional problem. There the eigenvectors have not changed, but it's when you do a 3-dimensional problem like combination of torsion and bending, and radial pressure, then you will not get anything like this holding for logarithmic strain. So this is, you can work either in terms of U or V, it doesn't matter, but in one case you are using eigenvectors in the reference configuration, in the other case they will be in the present configuration. Okay, so I think this again I have this bad habit, but you know, somehow in my class I manage time. In Blacksburg I manage time. One way I manage time in Blacksburg is because students start looking at the clock, so I know I'm exceeding my time. But you have been very kind, you have not looked at that clock, or at least I have not seen you looking at that. So that's okay. So we will resume at 3, and I will pay you back some time. So we end up before 5 o'clock because these people have to leave, and if we keep on talking after 5, then they are not on the tape. Okay, thank you, thanks.